here we go. This is my video explanation for the answer to this systems problem here. So, like we talked about in class, we are going to be approaching this problem from a couple different viewpoints, frameworks, you could say. At first, we're going to look at it like a system, right? A collection of these objects, and then we are going to start looking at them as individuals eventually. So we've got this Atwood machine here. We have M1 with more mass, M2 with less mass, and we're trying to find the acceleration of M1 and then the tension in that string there. To start, we got to find that acceleration. So we got to get the correct setup going here. I've drawn this pink shape to kind of represent the system that I'm looking at for this problem, this block M1, M2 system. So this is kind of the object that I will be analyzing. Now, in order for us to consider these as a system, we need to make sure that they have the same velocity, same acceleration. At the moment, as it stands, they don't have that. They'll be moving with the same speed, right, because they're attached to each other, but technically they'll have different velocities because one's going up and one's going down, right? So M1 here is going down because it's the heavier one, M2 is going up. So that's an issue. So we got to fix that issue, and the way we're going to do that is we're just going to pick a new positive direction. So what I mean here is I'm just going to change up those positive and negative axes. We said that we could do that if it came in handy, and we're going to do that right now. What I'm going to do is I'm going to set the positive direction as the direction that M1 is going in, okay? Meaning that I am going to say this is the positive direction. So M2 is going to move up in the positive direction. M1 is now moving down, but still in the positive direction. Okay? So for M2, up is positive and down is negative. For M1, down is positive and up is negative. And so now these objects do in fact have the same velocity and same acceleration because we've adjusted that. So that's going to make our lives easier in the future. Okay, we're getting close to being ready to find the acceleration of M1, but in order to do that, we're going to need to look at the net force acting on our system here. So let's pick a new color. Let's go with purple for this one. And what we're going to do is I'm going to draw the free body diagram for M1 and M2 in purple. And we're going to figure out what forces are internal to the system and what forces are external to the system. So for M1 here, I have a force of tension, and then I have Fg, force of gravity, and I'm going to label that as Fg1 because I know in the future, I know that M2 is going to have a different amount of force of gravity, so I'm just getting ahead of that there. Speaking of M2, again, we have force of tension, and like I was saying earlier, force of gravity, and we're going to label that as Fg2 because this is the force of gravity from object 2. So, looking at this, what does this tell me? Well, notice that my forces of tension are inside the box that we've drawn. Both of them are, meaning that that is an internal force, right? We also know that these two forces of tension will be equal to each other because it's the same string, right? And if it's the same string or same rope, it's going to have the same amount of tension across the whole thing, right? So those two forces cancel each other out within the system. So that means that our external forces, therefore, are Fg1 and Fg2. Those are our external forces. That's how we're going to find the net force acting on our system. Now, I'm not just going to add those two forces together, right? Because Fg1 is technically moving in the positive direction, whereas Fg2 is pointing in the negative direction. Okay, so one is positive, one is negative. Let's move to a new screen here. Color so you can actually see it. And let's now use everything we've done so far and put it all together to come up with an answer. Okay, so I'm solving for the acceleration of m1, which is also the same as the acceleration for my system. So net force equals ma. So I'm going to put a little s here to remind myself that I'm solving for the net force of the system. So that means I'm going to need the mass of the system, and I will have the acceleration of the system by the end of this. All right, so net force on the system, we said I have a positive Fg1, a negative Fg2 equals mass of system, acceleration of system. So let's swap these out with their respective equations. So force of gravity is just mass of the object times g, like that. So we have m1 is a mass of 3, g is 9.8. Then m2 is a mass of 2, g is 9.8. ms is the mass of my system. That means I'm going to take all the objects in my system and add up their mass for a total of 5, and then we're solving for that acceleration of our system. Plug this into our calculators, we get an answer of 1.96 meters per second squared. That is the acceleration of our system. It is also the acceleration of m1 because they're all attached together. So acceleration of my system is the acceleration of my object. Okay, cool. So this was question 1 here. Question 2 says, okay, now find the force of tension in the string. Now what I'm going to do is, because I can't use the system to find force of tension. The system says that force of tension is internal to the system, right? So it disappears. Instead, what I'm going to do is I'm going to just pick one of those objects, and I'm going to solve for force of tension like that. So let's pick object 1. I'm going to solve for the net force acting on object 1. In this case, I'll stick with my convention earlier about this is the positive direction, so I'll make down the positive direction still. So what I'm going to say is that I'll have a positive force of gravity and a negative force of tension times the mass of the object times the acceleration, or equals the mass of the object times the acceleration. So we have m1 times g minus that force of tension we're solving for equals m1 times a. Now I can plug in my numbers here. So m1 is, we said that was 3 times 9.8 minus ft equals 3, and we said the acceleration over here is 1.96. So we're going to multiply everything together. We get 29.4 minus force of tension equals 5.88. I'm going to add force of tension to the right side. I'm going to subtract 5.88 from the left side. I'll get an answer of 23.52 is my force of tension for this question. Got to put in units, so that's newtons there. So that's my answer for part 2 there. And I think this answer makes sense to me, right? Because looking back at my free body diagram for my system, my force of tension has to have some value between Fg1 and Fg2, right? That force of tension for Fg2 needs to be larger so that it overpowers the force of gravity on mass 2. And over here, this force of tension has to be smaller than Fg1 so that it, again, accelerates in that positive direction. So 23 fits because Fg1 is 29 and Fg2, I believe, is somewhere around 19, right? 19.6. So our number makes sense here. It works out, and so therefore that's a good check for us to make sure that we got the right answer. Okay, so that's how we solve this problem. Hope this was helpful. I'll see you later.